right, sorry everybody, a bit late today. So, I'm going to talk about advanced oxidation processes again today, and I think we've got lots of material here. Probably won't quite finish it today, so I plan on getting most of the way through this set of slides. I've got a few slides I still need to add some info to it towards the end, and then what I'll plan to do is pick up next time and kind of touch on a little more research-oriented stuff that I've been involved with in my academic career, and especially lately. So that's kind of the plan. So today we're going to take a look at kind of the more generic advanced oxidation processes and the kind of reaction pathways that we know pretty well. So that'll be hydrogen peroxide with UV, ozone with UV or with base, semiconductor photocatalysis, and then Fenton is probably the last thing we'll get to. And then next time we'll talk a little more about reactive halogens, single oxygen sensitizers, and quenching reactions with kind of non-target organics. A lot of advanced oxidation is targeted towards organic materials, but in the sense that it's, you're trying to degrade a pharmaceutical or maybe even illicit drugs that enter your sewage plant or something. Whatever it is that you're trying to control, trying to remove before discharge or use, that's typically what we think of that is our target removal. Of course, this is going to disinfect stuff, and in the case of photocatalysis, sometimes that is the target, is just providing some extra disinfection using sunlight. But in the traditional sense, advanced oxidation processes are there as, in some way, a polishing step to really destroy, oxidize, mineralize any last stuff that's in the water that we want to deal with, maybe that passes through a membrane or whatever other process we're using. Okay, so hydroxyl radicals, I think we talked about a bit last time, are the primary consideration here in terms of the most effective, or rather the most reactive species. So we're going to be talking a lot about hydroxyl radicals, and these processes that I listed today are all ways that we can produce them. So mostly that's what we'll be talking about today, and then we'll get into the other radicals later. Although, as you'll notice, basically with any radical chemistry, you're going to have all sorts of reactions that can branch, that can create intermediates or other radical endpoints that may have an impact or may be useful. And then what we're interested in typically is, well, what's the endpoint that has the most impact on our system? And usually if hydroxyl radicals can be formed, that's going to be the one with the most impact. We'll see in some cases if there's a bunch of dissolved organic matter, then perhaps these hydroxyls will react too quickly with the kind of generic non-target organic matter. Maybe it's natural organic matter and from a river or something, and will effectively have a much smaller concentration of effective hydroxyl radicals because of that competition. So maybe if we can use this more selective radical, that can make a difference. Okay. So on that note, the reactivity with organics has been pretty well characterized. There's a massive reference database that was published in 1988 about reactions with between different chemical species and hydroxyls or proton radicals, so H dot. So that reference list I'll show you in a moment. We can get all sorts of different reactions with, for example, tert-butanol. This one is highly reactive with hydroxyl radicals, so it's often used as a intentional quencher. So if we want to make sure that maybe if we're studying a system and we want to prove to ourselves that if we add something that reacts strongly with hydroxyls, then we'll see a reduction in the effectiveness. So that's maybe a control experiment that we design. This is one we'll use quite often. So you can think about the different reactions that can occur, in particular with organics, and hydrogen abstraction would be the type that you'll use, or that occurs with unsaturated bonds like the tert-butanol here, or like with methanol here. Both of those occur within hydrogen abstraction. So we have the hydrogen here, and essentially the OH takes that away, and then kind of that's how it's oxidizing this compound. And I'm not an organic chemist, so I'm not going to explain further because I would have to go and look it up again for you. But that is a common, hydrogen abstraction is a common type of reaction, and that's typical for hydroxyl radicals attacking saturated compounds that don't have the double bonds. Now, if we take something like benzene or some other bond that does have unsaturated bonds, so should have said unsaturated here, some sort of aromatic, some sort of aromatic compound, which maybe this is instead of hydrogen, we could say that's just some bigger molecule, and it's some group in that molecule, and that's what it's kind of talking about here with the R. The reaction there is going to produce basically it's going to be a OH addition. So it'll kick one of the, it'll take place of one of these hydrogens, and it'll add in an OH there to form essentially this guy. Now, one thing you'll notice here is there's still a radical. So there's still a radical on the carbon. So carbon-centered radicals are pretty typical with this hydroxyl radical reactions with organic compounds. That trend continues if we take a look at this reaction here. This is with methanol. Again, that's a hydrogen abstraction leading to that carbon-centered radical. And finally, the last type of reaction that may happen, and this is probably more common with inorganic compounds, but can happen with certain organics like oxalate, is you could just have a redox reaction. So rather than adding or subtracting from the molecule itself, what you can have is a change in oxidation state. So here we've got the hydroxyl radical, and it essentially takes an electron away, leaving this with a carbon radical here, or carbon-centered radical on the oxalate, and instead of 2 minus, it's just minus. So these radicals that are produced here, if we take a look at all those are going to be typically unstable. Not every case. Occasionally there are molecules that have some stability as radicals. In fact, that's one of our methods to learn about radicals, is to trap the different radicals into specific molecules that are very stable, and then they're called spin traps, and then you can learn something about, it's kind of like using NMR or like a magnetic resonance. You can then learn something about the radical that reacted with it, because it kind of keeps that spin for a long time. And the spin being the electron arrangements within the radical, they're unique. And we might touch on that a little bit more next time. So all these different types of reactions, and if we were to look at this reference database, it's really impressive, especially when you consider that they really didn't have the same word processing capabilities back then and reference management capabilities. So this was submitted in just a little bit after I was born, just to date myself there. And so in the 80s, probably they had something better than just a typewriter, but I'm actually not even sure. This might have been typewriter territory. And so then you look at this and you start scrolling, and it's like 1,000 pages of reference data pulled from other sources, basically tables and tables and tables. really pretty amazing if you think about it. That's pretty incredible. So anyway, this paper, this I guess reference database, essentially pulled all these different reaction rates of hydroxyls and the H atom, and I think hydrated electrons. So it's kind of like an electron in solution, which is also acts kind of like a radical. It gives some basic information at the front, and some good resources of generic reactions and stuff. And then it just goes into these tables and lists from all these different references and makes a note about, okay, what pH was used for them and the other particular considerations. So it's pretty amazing to think about where you get all these different reaction rate constants, and the fact that somebody went through and compiled all of these. You can see the rate constants are here for a given for the given compound, and that's in liters per mole per second. So second order reaction rate constants. Got the pH. Says something about the reaction or what it's being reacted with. So this table here, hydrated electrons with aqueous solution, and there's just several different tables, and then all the references at the end. So anyway, every time I go here to find some information, I'm always impressed. I mean, even if you did have Microsoft Word and everything, EndNote and stuff, it would still be incredibly impressive. A lot of work. So anyway, we cannot then think to ourselves that we can know every single reaction rate constant and have working knowledge there. So we need the lookup table. And in some sense, there's going to be pretty much an infinite number of organic molecules that exist. And so we can presume that there's so many different types of reactions that can occur. When you get into larger macromolecules, dissolved organics type of stuff, then what you're really going to start thinking about is, okay, well, what about the little functional groups at the edges of these molecules, or that are composed, somewhere within the molecule? Which ones of those are most reactive, and how does that affect the system? Okay, so just grabbed a couple from that paper here to show you benzene. Just as an example, the references listed were 7.8 or thereabouts times 10 to the 9th liters per mole per second. And it turns out that these are diffusion controlled rates, or we consider a rate constant diffusion controlled if the limit to how quickly it's reacting is limited by how quickly the molecules diffuse. And so it turns out that the lifetime of a solute, so let's say the lifetime of a hydroxyl radical, is going to be about 10 to the minus 7 seconds. So it's like 0.1 microsecond or 100 nanoseconds. If the concentration of the solute is 10 to the minus third moles per liter. So that's at a diffusion controlled rate. So that gives us a little bit of perspective on, okay, if we had some concentration, so 1 millimolar concentration of some reactive species, it's reacting at a diffusion controlled rate, then we expect a lifetime of 100 nanoseconds. So some perspective there. Now, it's very rare to have something like hydroxyl radicals anywhere near that type of concentration. Typically, you'd be thinking like 10 to the minus 12th moles per liter, something on that order. And that's just simply because they react so quickly. This diffusion controlled and solute concentration, this would be more like, maybe a better way to think about this is if your solute, let's say benzene, if you had 10 to the minus third benzene in the presence of a diffusion limited reaction, enough hydroxyl radicals to create the diffusion controlled situation, then the lifetime would be here. Maybe that's a better way to conceptualize it now that I'm thinking about it that way. So regardless, it just kind of shows they react really quickly, and whenever we get to solving problems with kind of the second order kinetics, we'll see, these rate constants cause things to happen really quick. And in general, with hydroxyl radicals, it's typically diffusion controlled. Some of the other radicals, particularly singlet oxygen, we'll see that maybe it's not quite diffusion controlled, or there's at least the single oxygen typically diffuses further into solution depending on what's in solution. But just wanted to kind of introduce that, remind us about how quickly really they do react. So here's a figure from our books. It's kind of showing different sources and sinks of our hydroxyl radicals given some generic advanced oxidation process. So we have, this gray box here as the pool of available hydroxyl radicals. And so anytime we're producing it, maybe we're photolyzing hydrogen peroxide, then that's contributing here. And so in this case, we see the different reactions coming from that. So we have this hydroxyl radical, and that's going to react. So these three different reaction pathways here, and it's giving us three different cases. One is that terbutanol that we looked at. One is the aromatic compounds we were talking about. And the last one here is methanol, if I've got this right. No, that's not right. This one's, what is this? I should know. Does it say? Yeah, okay, so sorry. This one's terbutanol, and that's methanol. Okay, yeah. That makes sense. Haven't had coffee today, so not promising that I'm all the way awake. Okay, so if we take a look at these reactions in this system, one thing we'll notice is we actually, sometimes that carbon radical that we end up with. So this the methanol here, when we react, we're going to end up forming an oxygen and ultimately having this radical that can then end up converting back into proton and superoxide radical anion here, O2 dot minus, which can then have some conversions back into hydroxyl radicals to loop back into the system. Now, you're probably going to have a net loss, I believe, but you do end up having some contribution back into the radical pool. For the aromatic here, we've got a similar situation where we've got we end up kicking off an oxygen, got this new compound, and this one actually has an oxygen-centered radical here. At this point, it was carbon here. Then this, we have a reaction, again getting that superoxide radical anion, and can go back up to hydroxyl radicals. So sometimes these are a little bit cyclic, and so you might end up with almost a catalytic process where you're probably consuming 2 hydroxyls and returning 1, or something like that on the net scale, and if conditions allow. Sometimes things like that, superoxide radical anion requires an electron donor to form in the first place, and then so you might be consuming part of your substrate in doing that cycle. Terbutanol, however, and this is one of the reasons why it's so effective at quenching hydroxyl radicals, has no cyclical nature. So if we have a reaction there, and we follow that down, we end up with this net sink, and this little symbol is is used for the sink, and we have no single superoxide radicals produced, and no other ways of replenishing the hydroxyl radicals. A lot of these reaction pathways hold true or similar for atmospheric reactions, so you can kind of think about that as, you know, the cyclical nature of lots of photochemistry in the atmosphere. This is why chlorofluorocarbons are not so good for our ozone layers, because they catalytically degrade ozone with processes like these, and it takes a very long time, but very many cycles before they actually degrade into something that can no longer go through that catalytic reaction. Okay, so let's take a look at UV and peroxide and consider what that implies and entails here. So the key pieces about an advanced oxidation process driven by UV light are going to be really the quantum yield and the molar absorptivity of the oxidant that we are splitting. So typically for an advanced oxidant, we are going to take a molecule that is already kind of good at oxidizing stuff, and then either through some sort of catalytic process or chemical process or through UV, possibly heat, we're going to cause it to break apart into radical components. So that's exactly what we're doing with UV and peroxide, where we've got the UV light here that we usually write it as HV, and that's going to give us 2 hydroxyl radicals for every time we have that photolytic reaction happen. One thing to keep in mind is hydrogen peroxide does have an equilibrium reaction, and it can form this HO2 minus and H plus. It's a lot like water, you know, it's forming acid and base. So we do have that in play here. So if we take a look at the molar absorptivity here, or this is, I guess, just light absorbance by different concentrations of hydrogen peroxide, what we see is essentially it's absorbing right around 250. So this range here is the peak absorption, and again, this is just normalized to itself. I pulled this figure off the internet somewhere, just to show you where peroxide absorbs. So light in this range then it will absorb and will cause this splitting. It turns out that this guy, I don't even know what it's called, HO2 minus, absorbs more strongly. So if we were looking at an absolute instead of a normalized spectra, we'd have something where, you know, and I don't know the shape, but we can imagine maybe something like that for the HO2 minus. So essentially, under, you know, if we have conditions where we have a lot of that, which would be, you know, that condition then would yield lots of this stuff absorbing light, which is going to be a problem, because then we're not getting 2 hydroxyls from it. Maybe we still get one if there's that photolysis can occur, but it's not. It's just not ideal. And so the controlling of the pH then is important, because then we can control how much is in hydrogen peroxide versus this version. And I wrote here that basic is best. And thinking about it right now, I'm feeling like that's the opposite. I think it would be acidic is best. So I'm gonna double check that fact and come back to you on that later. At any rate, the overall, you know, just considering the peroxide itself, the overall quantum yield for, you know, how many hydroxyls do we get per photon tends to be just a little bit above 1, so 1.11 under normal conditions with a UV 254 lamp, so the typical mercury fluorescent lamp. And so that means that most of the photons end up splitting it, and the effective result is a little over half of them result in a split to two of the hydroxyls. Because if it was perfect, then our quantum yield, I think the way it's defining it would be 2, because we would have 2 hydroxyls per photon. So quantum yields are very often important as part of this analysis here. Okay, so the other thing that can happen is we can get these superoxide radical anions as kind of we saw them a moment ago in the previous reactions. If we have something like that forming, or perhaps the hydroxyls may react with something and form those, we can end up reacting those with acid and getting this guy again, which is in equilibrium with hydrogen peroxide. Oh wait, no, I'm sorry, that was not the right one. That's a radical, but that one can end up reacting probably with water to form peroxide and oxygen there. Okay, so that component here, I think I've got it here to talk about it, because that is a way we can end up reforming peroxide in some cases. Okay, so if we were to take a look at the kind of hydroxyl radical sources and sinks for a typical peroxide UV system, obviously we're adding hydroxyls with this reaction. So we've got hydroxyl radicals adding to the pool there, and then we're going to take a look at 2 important reactions here, one with methanol and the other with bicarbonate. So bicarbonate, and we'll talk more about the quenching and unwanted reactions next time, but bicarbonate and other weak bases tend to react pretty strongly with hydroxyls and can be a problem that way. So we definitely don't want lots of carbonate in our systems if we're trying to apply these OH radical AOPs. Okay, so then we have several different reactions that can occur. I think these are defined in our book, which we could take a look, but essentially different reactions. So whatever G1 is, quenching, G2 can end up forming more hydrogen peroxide, which goes to our peroxide kind of pool, so to speak, which then can go back with the UV added and form more stuff. It can also lead to a net quenching if the hydrogen peroxide goes and reacts with something maybe in solution, which, we use peroxide in our households because it does have some bleaching type properties. And actually it's Fenton chemistry that we use when we pour it on a cut. We'll talk about that in a little bit. So if it reacts with something directly, then we've got a net sink there. Other reactions, whatever G4, G5 are, can quench it. But methanol here, if we take it down to this point and have this reaction, we can end up having hydrogen peroxide and oxygen form we saw a moment ago. So we can have that to replenish the peroxide in some cases. So it's, as you see, each one of these systems is pretty complex, lots of reactions going on. So to understand it and characterize it well, we do want to know something about all these different reactions so that we understand where stuff is going. But at the end of the day, a lot of times it's, we're not necessarily going to model each and every one of these for a practical system. It's probably going to be a little bit more heuristic, meaning we kind of trial and error, like how much does it take to achieve this goal, rather than calculating all of these reactions with their rates to decide how much hydrogen peroxide to add today.
So, well, hydrogen peroxide, but It must be a different wavelength, 'cause I thought it was degraded by light. That's why it was in a brown bottle.
No, that's exactly right. So it does. We do put it in a brown bottle. We actually put bleach typically in opaque bottles as well. So it doesn't have much here. Doesn't show up much, but there is enough here
Like in the visible, or
that's reaching up to the visible that over time it will cause that reaction. So in part it's also just that peroxide is relatively unstable. So anything that has some instability, maybe some other molecule gets kind of excited and then reacts with it quicker. So if there's something in there in addition to the peroxide, or so in,
I just heard like if you left it out in a clear bottle, it would just turn to water.
yeah, and it will. It's not it's not going to be like if you shine
Water
this
hydrogen gas.
right. If you shine this type of light on it, that'll happen a lot quicker.
Okay.
Right, but you're going to have a little bit of the same stuff happening. Yeah. You can actually also add acetic acid or vinegar, and then that ends up you're in equilibrium with something called peracetic acid, which is one of a kind of a newer disinfectant that's used for wastewater treatment lately. You'll have some peracetic acid and some hydrogen peroxide in water. So that's kind of neat. There's potential to use that for advanced oxidation as well. So maybe if I might look into that to talk about it a little bit on next time. But yeah, you're definitely right that is another potential sink for the peroxide if you were just to have it at home. Okay, so another process that we actually touched on last time is reacting ozone with hydroxide, so not hydroxyl radicals, but OH minus. And that reaction, again, we looked at several reactions last time, and we can end up forming hydroxyl radicals after a sequence of reactions. And so if we take a look at what happens if we're using this, and again, it's kind of an example to just look at the rate at which something's going to degrade given some reasonable conditions. The figure on the left here, this is the fraction of oxidized compounds mediated by hydroxyl radicals. So the fraction, so some degradation happened. What fraction of that was mediated by hydroxyl radicals compared to ozone itself? So ozone can react with stuff, and these hydroxyls are reacting with stuff. So we're looking at what fraction was the hydroxyl, meaning if we look at the top, anything up here, all of that action was done by hydroxyl radicals. And on the flip side at the bottom, any degradation that happened occurred due to ozone itself for at the bottom. Okay, then on the x-axis, we have a ratio of concentration of hydroxyl to ozone. So as we increase there, we have a higher ratio. Now, if you look at the numbers, 1 to the -6, that means our ozone is 1,000,000 times more concentrated than our hydroxyls there. But that's at least a lot more than, one in every, I guess, 10 trillion, 10 billion, sorry. Yeah, so that ratio there, it is, while it's small, that means that we have a very large portion of, comparatively large portion of hydroxyl radicals as we move to the right. Okay, so that we can take a look at different compounds. MTBE, that's a common additive to gasoline. Don't remember exactly the acronym right now. So that one's degraded pretty quickly, and we see it's degraded pretty well by even just a little bit of ozone, but certainly faster with more hydroxyl. And these different compounds, this one's carbamazepine, I looked, and different ones, we can see ozone is really not impacting some of them almost at all, right? The ratio that, or excuse me, hydroxyl radicals, ozone is doing, yeah, I think I said that backwards, sorry. The ozone is doing all the work when we're down low. So MTBE then is not degraded by ozone, and it's only degraded once we have, it's degraded pretty easily by hydroxyl radicals, but I think that's the way to interpret this. So then something over here on the bottom right, let's take this MCLR. It's degraded by ozone, and only once we have a lot of hydroxyl radicals do the hydroxyl radicals start making a bigger impact than the ozone. Okay, so then in some sense, I think that the further left we go, the more resistant to ozone it is. Yeah. But the hydroxyl radicals typically will do it eventually. Okay. So taking one of those, this next figure, this is atrazine at pH 6 and 7. It's the same data on both graphs. They just changed the x-axis so that we could see it a little more clearly. Because if we look at graph B here at pH 6, and this is over some amount of time, given 20 micromoles of ozone, so we expect that at pH 6 we'd have just ozone, and pH 8 we are getting hydroxyl radicals. That's the way to take a look at this, right? And just to take a look at the kinetics there, we see that the hydroxyl radical kinetics are much faster, right? That's on the order of seconds given these conditions versus 600 seconds, 10 minutes for the ozone to reach to do a similar amount of degradation. So, and especially if you take a look at exactly, what remaining concentration in nanomolars here we have at the end, it looks like, 4 here. If we take a look at how long that takes for this, 5 seconds compared to 600 seconds. So that's quite a big difference. Okay, another thing we can do with ozone is blast it with UV. And we talked about this a little bit when we were talking about UV in general. But essentially the key reactions here are just ozone with the UV light. We'll get oxygen and an oxygen radical, so O dot. Now, there's a lot of distinctions about this O dot, and I'm pulling some information from a paper here. And you'll see these types of nomenclature when dealing with certain types of radicals, and it's really describing the energy level of the electrons, the unpaired electron. And so this O1D is a more reactive one. That one can form hydroxyl radicals. This O3P is less reactive and cannot, if I've got my memory straight here. So you can form that O dot, and it's a bit wavelength dependent here, and I'll come back and explain that in a moment. But essentially, when we have this generic reaction, this other set of reactions from that paper, what it's essentially describing is, well, yes, this is happening, and this can happen by all sorts of different wavelengths, but you're going to get a different flavor of these species. You can have O2 that is a singlet excited state, or it can be just ground triplet state, and there's different levels of reactivity or levels of excitation that electron can end up at. We'll talk more about singlet oxygen next time, but that it is a reactive species. It's not technically a radical, like the O dot is a radical, and it does get confusing because it's the O dot is a singlet oxygen atom, so we would maybe call that a singlet oxygen radical, whereas if we have molecular oxygen that is excited to the singlet state, then we call that singlet oxygen. So it's a little confusing there, but the point is, if we take a look at the wavelength, so
Do they have the same energy?
Yeah, so the different wavelengths correspond to different energies, and so when we split it, there's different energy levels for these different versions, right? So this one delta here is high energy. Let's see, I think it's the triplet sigma here is the lowest energy, and I want to say the singlet sigma is the highest energy, which then usually goes to that state and goes to that one. I think that's the order in which things happen, or something like that. And what you'll notice here is, given the, there's like both pieces have energy levels. So if you have a really high energy photon, you get two high energy products, this one being the higher energy of the oxygen radicals. So this is high energy, and this is fairly high energy. And then if you go down the next, and that's the lowest wavelength, so the highest energy photons that split it. If we go to the next highest level energy, we get this guy, which is again the high energy radical, and the not so high energy oxygen form. I think this might even just be ground state. Can't remember. With an extra electron. No, that doesn't make sense.
We'll say it would be a ground state.
Yeah. I'll take a look into this. I'm going to add some more content. I should. I think it's the electron orbital SPDF stuff.
That makes sense.
And then when you pair, I think it has to do with which orbital the electron belongs to that's excited.
Okay.
And then the 1 or the 3 is essentially the spin. It's the spin state. 1 meaning there's only one spin state it can occupy, and the 3, there's 3 different arrangements that it could be just based on the situation. I'll have some visuals next time about that to talk more about single oxygen. It really is. Point being, though, that you can get this single oxygen, that excited diatomic oxygen, so our molecular oxygen, and you've got this oxygen radical, and that oxygen radical, you can react that with water to form peroxide. So if you've got UV coming in and you have ozone, you'll get hydrogen peroxide, which means you are going to get your hydroxyl radicals from that, then photolyzing if you've got enough energy in your wavelength there. You can also form, react ozone with this guy, which was a conjugate base of peroxide, and form some sort of ozone radical and this radical. So there's several reactions that can propagate, and you'll essentially have the potential to be forming hydroxyl radicals through these pathways. Okay, for the quantum yields, this sigma here, for the production of, I'm just going to erase this for now. Production of this guy with wavelength that's like 310 or less, you'll get a pretty good quantum yield. This is pretty well documented. Quantum yield of that oxygen radical, right, in the reactive form, that is nearly unity, nearly 1 for 1. So 1 photon, 1 resulting radical here. And this paper that I cited here, and I got this from, really what they were looking at is, well, we all, their perspective was, we all know this happens if we take, let's say, UV254, and we know that, we get the radical chemistry that we've been talking about right now. But UVA should be able to do it to an extent too, kind of like that example of leaving the peroxide in the sun. And so they were interested in, another source of that same radical just at lower wavelengths. And it turns out that what they were looking at is kind of the 320 to 400-ish range, and I guess maybe this is what they used, 411. Anyway, this reaction has a quantum yield of 0.064. So not very effective, but still capable to get that same chemistry. And it kind of makes sense if you take a look at the ozone absorption cross sections as a function of wavelength. You have this area here that was kind of this suspect range about kind of the low effectiveness, whereas normally if we're doing photolysis for water chemistry or water treatment, we've got pretty good absorption. And then you see ozone does absorb higher bands, but that reaction's not going to form this O1D. That's going to be the weaker version that's not going to end up creating hydroxyl radicals. So that's what we see up at 611 or 1200.
Yeah, that's why plants absorb. They evolve to absorb. My other professor in my light class was talking about that. How like the O3, how it has that gap right there in between the 350 and to about 500, because 500 is green.
Yeah.
And it peaks up there, and then it'll absorb again in the high red for like chlorophyll. Yeah. But he was talking about the gaps and like certain things. He has this giant chart where like, there's a gap here.
Yeah, so
interesting. Kind of like something like that. Something small, like it's because it doesn't absorb it that it allows for other things to absorb it.
Right. Yeah, there's it's really fascinating to see that type of thing, because it's like, oh, so it's making use of the opportunities afforded by its environment.
Yeah. But also it's crazy how if you didn't have these other things are oxygen, absorbing into such high low
high energy photons. We'd be having a hard time.
Yeah.
Basically, we'd probably have to live underwater or something.
So I didn't mean to distract you.
No. Enjoy it. It's good. Okay, so if we take a look at, again, the sources and sinks for this system, we've got, again, a way to end up with a hydroxyl radical pool. In this case, we're taking a few more complicated steps to get there. If we have ozone here, some reactions can get us that HO3 dot. That can go through some reaction, get that O dot, react that with, I think that isn't a hydroxyl radical, and then that hydroxyl radical, not sure what that means here. Anyway, we're forming hydroxyl radicals, whatever's happening here. So there's a few different ways we can see. Honestly, don't know what's going on this left side of things. Why we have two separate spots with ozone. Maybe that's just a separate pathway to get to this different types of ozone initiated reactions here. I don't know why they drew it that way instead of just, I guess, I don't know. Anyway, so we get this, we have routes, complex routes to get from ozone into the hydroxyl radicals, and then we can go from there, and we're taking a look at, again, reactions with methanol or bicarbonate, and it will end up looking pretty much quite similar to what we were looking at a few minutes ago with the UV peroxide, different sinks, and potentially replenishing of a radical species that participates in the formation or the reformation of hydroxyl radicals in combination with the ozone. So if we look at enough of these, we see some similarities, that there's lots of stuff going on, some cyclical and some endpoints or sinks. And so that's really the point of a lot of research in this type of area, is to better understand, okay, what are the sources and sinks, and what are the most important ones. Okay, so I want to talk about another way we can form hydroxyl radicals and similar ones, and that's photocatalysis. This is something that's received a lot of attention in the past few decades, because you can take a semiconductor and expose it to light, and potentially even visible light, or kind of near the edge. If we improve it enough, then we can have some decent yield at visible lights, but typically you kind of need a little bit into the UV for the energy. And essentially what you're going to do is excite the TiO2, for example, or whatever other photocatalyst you have, which zinc oxide, this guy here, SB. What is SB? I'm blanking. This is antimony? No. I should know this. Huh?
Thing sunscreen?
No. What element is SB? Antimony. Okay, so then we have some antimony oxide and ceria oxide, or cerium oxide. So different materials can do this. This is not an exhaustive list or anything, but
Must be one of the ones with the bottom.
yeah. And so different molecules, or different semiconductors can do this. And essentially what happens is when we excite them, we split off an electron. We kick an electron from the valence band, and it kicks up into the conduction band. And then from there, both of those components can react with either water or oxygen in the water, or some other stuff. Can potentially react directly with something we're targeting. We could directly oxidize or reduce some compound. But generally, both the electron and the hole, this H+, we'll say, we'll call that a hole where the electron is missing. Both of those can end up giving us hydroxyl radicals, one by transition from oxygen to superoxide radicals, and the other by directly oxidizing hydroxide. So that's a photocatalysis in a nutshell. Get these great highly reactive radicals from the surface of our catalyst when we expose it to light. We're going to talk about a lot of different challenges. One of them is direct recombination. So if we have these two split, well, they could just recombine and release some heat. So there's different innovations in materials design aimed directly at preventing that splitting, letting these reactions or similar reactions occur before that happens. So we could take a look at the net reaction, by the way. TiO2 with the light, we get the hole and the electron and the valence band or the conduction band. These two can collapse back together with heat, or ideally we have water reacting with that hole, get that hydroxyl radical and a proton, and the hydroxide reacting with the could also react with the hole directly, or we can have oxygen and that forms a hydroxyl radical, or we could have oxygen reacting with the electron there and getting our superoxide radical anion. As we know, that can participate in further reactions and can get to our hydroxyl radical. This is very similar to what we do with solar cells, except that we limit what is touching them. So we don't want any of these reactions because that'll degrade our solar cell. So we actually want it all in a very carefully controlled, no water, no oxygen type of environment. So then we harvest that conduction band electron and send that through our system. That's essentially providing the current, and the whole loop is that it's we have a ground to supply extra electrons coming from the valence band. So we've got some voltage based on that potential difference, and we've got that current coming off with electrons coming out. So kind of a similar system, and you will have heard of photoactive semiconductors in that sense. A few reactions here. So in a bench scale experiments with TiO2, we're going to take a look at the paper this came from in a moment, but this is just a few examples here of essentially the quantum yield for the degradation of these products. So how many molecules are degraded per photon we absorbed with our catalyst. And if we take a look, different experimental conditions here, but the quantum yield as a percentage for coumarin is 0.36 to 0.27 with a different wavelength here. Methanol is 4, so that's 4%. Rather than, we could write that as 0.04 as a ratio, but this is quantum yield as a percent here. So overall, these are pretty low for these conditions. So one thing I want to note here is that the overall yield of effective reactions are pretty low. We'll talk more about this in a moment, but the other thing is they have to react with the surface. These radicals can't go too far from the surface. That's one of the challenges. So there's a couple good papers. Both my PhD advisor was involved with both. That's Jae-Hong Kim here. So one, this was I think 2016, came out and was taking a look at how we apply these for kind of portable or resource scarce disinfection applications, solar water treatment, and what's coming down the pipeline, what are the limitations. And this one in particular, assessing the efficiency limits for advanced technologies for solar water disinfection. So definitely highly recommend looking at that paper. One of their figures here takes a look at, okay, we've got solar energy. If that's our basis here, then that gives us some available number of photons, different wavelengths. And so there's a few options we can use. We can use a photocatalyst, aiming at hydroxyl radicals and other readily available ones with that, but mostly hydroxyl. And we've got brackets here. We'll achieve some pseudo steady state concentration given some conditions. The photocatalyst, while being irradiated, will continuously produce them. And then, as we know, they react really quickly. So there's going to be the source and the sink there with the production of the catalyst and the sink of whatever reactions happen. So we'll have some steady state assumption, and then we can get a CT value just from, like we were doing with our chemical disinfectants. We can say that, we have some amount of radicals. We'll assume that's constant because we're continuously producing. Then we can figure out how quickly do these radicals react with our bacteria or our virus. And we can have that CT concept in effect. Then there's a question of how long are we letting it sit there and all that. We can do the same thing with photosensitizers. These are typically things that we're producing that singlet molecular oxygen. It's reactive, less reactive than hydroxyls, but still useful, especially for disinfection. We can compare that with direct SODIS is what we call it, solar disinfection. So just using the UVA and whatever UVB might happen to make it there as a source of inactivation. Usually what that's actually doing is not a lot of the dimerization of DNA, but rather using cellular components as single oxygen producers or other, photosensitized reactions happening within cells and essentially disrupting and causing oxidative stress within cells, kind of based on that route, the single oxygen route or similar. So that just kind of matters about how much time you give it, and increasing temperature tends to help a little bit as well. You could potentially use some other fancy methods. This one here is up conversion. Turns out that is really not very efficient. It was a neat idea where you can take multiple photons from a low energy, like yellow light, and then up convert them to a higher energy, like, from yellow to like blue, or from blue to UVA, or in this case, UVA to UVC, and then use that UVC. Turns out that's not practical, but it is a neat idea. And maybe there's innovations to be had there at some point, but I don't think it's going anywhere as far as I understand. The other thing you could do is just use a solar cell and then use that electricity to drive maybe a UV LED for that. So they took a look at all these different factors of solar water disinfection, and it really is kind of a neat topic because it really ties in a lot of the stuff we've been learning over the past couple weeks. So definitely recommend that. It's a short paper. It's a letters, and it's a rather general paper as well in terms of the topics. Don't get too heavy into it. So definitely recommend that paper. The other one, talking more about the limitations of photocatalysis in general. And this one's, it's funny, my PhD advisor is also a little bit of an artist, so he drew this picture and the cover art picture, which I don't have there. He's a funny guy. I like him. So this one's the technology horizon for photocatalytic water treatment, sunrise or sunset. So really taking an analytical approach to, is this stuff going to actually be practical, and what would it take? So there's a lot of big names and a lot of people that have worked in this area. This was 2019, so certainly another I think impactful paper here. And so they took a look at different energy conversion, the quantum yields I showed you a minute ago, and kind of took an approach to find the overall efficiency. What were the limitations? What are we doing? How good can we get here? And comparing that to kind of standard, let's say, electrical to UV lamp type of systems. Okay, so we have that. We have then, if we're going to use the lamp to then excite a molecule or a sensitizer, photocatalyst, whatever, we can see the efficiency drops, right? We have some efficiency drop from converting the electrical energy and sending it down, down the system, from the power plant, from whatever, combustion or whatever is generating the power, through the lines to the lamp. Then the lamp is only so efficient, or the LED, and then your catalyst is only absorbing so much. Could also just use sunlight, perhaps. So how many of those photons are absorbed in that case? Then here it's saying additional loss due to light absorbing matter in water, so dissolved organics. Some formation efficiency based on that whole recombination. Even though we can improve that whole recombination, the big picture is maybe that's not enough. Maybe there's other efficiency gaps that are important. So they really took a look at the different sectors of this type of technology that can be improved, and kind of their overall energy efficiency that they kind of concluded here. So for photons or electricity into hydroxyl radicals was somewhere between 0.0002% and 2% using UV lamps, and a bit less than that using sunlight. And that's so that's a couple of the pathways there, or less than 5%. I guess in addition to that, less than 5% of hydroxyl radicals available for pollutant degradation in natural waters due to scavenging by bicarbonate and natural organic matter or other constituents. So lots and lots of reasons that it's not as efficient as we'd like it to be. And so in my view, this figure is not even capturing one of the more important ones, and that is, if you did have lots and lots of radicals produced and in an efficient manner, you still have a big problem of your reactor design, which is something that they do talk about, but not in this figure. Reactor design is important because the radicals are only going to diffuse so far. So you have to have a system where there's enough contact time. So if you remember that other figure from the other paper, that contact time is what's going to determine how effective this is at degrading a pathogen or a pollutant. You have to have the radical and the chemical or the pathogen together in order to have the reaction occur. And if these radicals have such short-lived lifetimes on the nanosecond scale or something, they're only going to diffuse nanometers into solution. So when you consider how to create a photocatalytic system, you either have to put it into like a batch type thing with a slurry with catalysts everywhere. Then you have, okay, well, how far is your light going to go through when you're adding this catalyst that's absorbing it? Or maybe you coat some surface. It has to be able to be exposed by light. You want it to be high surface area, and you have to have enough the chance for the water to flow across it and everything. So in a very pessimistic view, sometimes I think, well, yeah, why even try? However, this is my topic of research to a large extent. So what we've been aiming at is taking that cynical perspective and then saying, okay, well, what are the biggest diffusion limitation issues? So dissolved organic matter was one that I was able to kind of start working on. And can we better understand how much quenching is going to happen based on surface adsorption of organics that are not what we're targeting? And can we do something to control that? Also been interested in kind of the UV LED side of things and as that relates to these different processes. Yeah.
How is the sunlight like applied in these systems? Like, is it just the photocatalyst is like how do you apply sunlight to the titanium oxide that was reacting?
Yeah. Well, and that's exactly what I was kind of getting at in some senses. Like, how would you design your reactor? You want it exposed to light. You want the water to be passing through at the same time. And so there's been some clever ideas. You can have, let's say, a fixed bed of some sort, and then coat it. Let's say you coat this with TiO2 or something, and then you essentially allow water to flow. Maybe angle this.
Like a top down.
Yeah, this is top down view, and then you have sun shining from above. We'll give it a little bit of a 3D feel here. So like putting like a pipe or some baffled system where you have TiO2 onto that surface, light shining down on it, so you'd angle it towards the sun and let it flow through.
I wonder if there's anything with like fiber optics that would be.
I was about to say there's one of the most clever reactor designs I have seen is a coating fiber optic cables, and it's actually something that I've kind of been wanting to pursue and haven't done yet. So there have been a couple studies taking fiber optic cables, and so a typical fiber optic cable will look something like this, where we have some sort of casing that is normally there that goes across. The cable's inside, it's a kind of glass type material. Probably you want something that's a fancy quartz for transmitting far UV, but typical glass is going to work for UVA, which is what we can use. So typically it's this casing that provides protection from it being too brittle and breaking. Now, I mean, that glass in there, anything that's thin enough typically can be bent without breaking. And so with this extra casing, it keeps it protected enough that fiber optic cables can be bent, even though it's like glass inside. That said, if you're ever working with fiber optic cables, be ginger with them. You know, don't crease them, because that will definitely ruin them. So just a kind of side note there. But what they did was they removed that cladding, or that casing, and then coated TiO2 on that surface, then just kept them straight and allowed for light to be shining through, and it would bounce through. Some of it would escape each bounce and be absorbed by the catalyst. I thought that was probably the best case that I had seen. And what I would like to do is use a polymer fiber optic cable and potentially use a sensitizer rather than a catalyst on it. Because if you use a polymer based, like a plastic type, and you've seen these little things in little knick-knack stores or whatever, where you have little fiber optic cables and a light source, and it just kind of changes the colors or something, and like old Christmas trees or whatever. They're kind of cool looking. You could potentially do that same thing with a plastic one, and those are plastic. You could bend it, so you can spiral it. You can, if you bend it enough, it actually causes more light to leak out, so you can optimize it based on the bend. And the problem would be, if you're using a catalyst, you might have the radicals attack the polymer. With a sensitizer, some polymers are resistant to single oxygen and that wouldn't be too much of a problem. So that's what I'm thinking. You kind of need the glass for a catalyst or something like it, because it wouldn't be the glass would be resistant to the hydroxyl radicals. Yeah, so that's actually what I was planning to describe here on this slide, is that diffusion limitations, reactor design, how to overcome that. There's a lot of different challenges, but that's what I think is really the real reason we haven't had practical application, is because it's just not, in combination with the fact that it's low efficiency, we just don't have a smart way to keep the catalyst there, to expose it to light and the pathogen or whatever, and keep it away from getting washed down through the system. So, all right, so that's all for today. We will pick up here next time.